everyone. I am Dr. Aurora Elmore, the Cooperative Institute Manager for NOAA Ocean Exploration. Thank you very much for joining us today for NOAA's Science Seminar. This is the third webinar in a 6-part series about NOAA's Ocean Exploration Cooperative Institute, also known as OECI. Throughout the webinars, we'll meet the OECI team and hear about their groundbreaking projects in deep sea exploration. The OECI is a partnership between NOAA, the University of Rhode Island, Woods Hole Oceanographic Institution, University of Southern Mississippi, University of New Hampshire, and the nonprofit Ocean Exploration Trust. For some general information before we get started, this presentation is being recorded and will be posted with closed captioning shortly after the webinar. Live closed captioning is available now, and the link has been posted in the YouTube description. We encourage the audience to ask questions and for those to come in throughout the presentation. You'll be able to ask questions in the live YouTube chat box, but you must be signed in to YouTube in order to do so. So for those of you with a NOAA.gov email address, in order to ask a question, you'll either need to sign into YouTube with your personal email address, or you can send an email with your question to oeci_questions@uri.edu. And now, to start today's presentation, I'm very pleased to introduce Tara Hicks Johnson, Outreach Specialist from the University of New Hampshire. Tara, over to you.
Thanks very much. Welcome, everyone. We are coming to you from the Center for Coastal and Ocean Mapping at the University of New Hampshire, one of the partners in the Cooperative Institute. The Center for Coastal and Ocean Mapping, or CCOM, is a national center of excellence focused on the development of new technologies and new approaches for mapping the seafloor and the water column. We're a group of more than 120 researchers, students, and staff focused on supporting NOAA and the nation in a range of ocean mapping, exploration, and characterization tasks, both in shallow and deep water. And we're thrilled to be partners in the Ocean Exploration Cooperative Institute. So today, we're going to focus specifically on the work that CCOM is doing as part of the Cooperative Institute. And to begin these discussions, let me introduce you to the director of the Center for Coastal and Ocean Mapping, Larry Mayer.
Well, thank you, Tara. You know that I'm always happy to talk about what we do here at CCOM, but I'm particularly delighted today because I get to talk about our role in this really wonderful adventure that we call the Ocean Exploration Cooperative Institute. This is now the fourth in our seminar series on the OECI, and in the first seminar, you're introduced to the concept of the Ocean Exploration Cooperative Institute. This idea of a community of partners working hand in hand to develop technologies needed to efficiently and effectively map, explore, and characterize the underwater territory of the U.S. And in doing this, we also want to engage the public and inspire the next generation of ocean explorers and blue economy professionals. All of the partners of the OECI have had a long and really quite successful history in making contributions to these goals. But the OECI raises these efforts to a new level. It brings us all together to work collectively and collaboratively on these important but also very ambitious goals. And while each of our centers have our individual roles and our areas of expertise, it's really this collective of the whole that will set this effort apart and certainly make it much different than efforts that we've been involved in the past. In the second seminar of the series, we focused on the work of the University of Southern Mississippi and the use of their autonomous underwater vehicles, Eagle Ray and Mola Mola, and their collaboration with Tuskegee University. And the Inner Space Center brought you a live broadcast from the USM vessel Point Sur as they searched for the wreck of the Norlindo. And in the third seminar of the series, you got to witness a tech demo live from the Ocean Exploration Trust's vessel of exploration Nautilus, where the Woods Hole autonomous underwater vehicles Nui and Mezabot were for the first time integrated with the Nautilus, and most excitingly, began to demonstrate the first steps of acoustic and optical communication between the vehicles and the ship, and the demonstration of the ability to control the vehicles from the shore. And I think you can all remember the excitement in the voices of Jason, Megan, Dana, and Andy, as not only did the systems perform well, but most importantly, we were witnessing the very first tangible steps in addressing one of the important goals of the OECI, and that's to start laying the groundwork for a really new paradigm of ocean exploration that takes our expensive manned research vessels and uses them not only as a platform to conduct their own research, but simultaneously allows a suite of autonomous systems to extend the exploration footprint and conduct multiple coordinated mapping, exploration, and characterization missions. And in doing this, we can greatly increase the efficiency and the effectiveness of our exploration efforts. And this is a goal we're really, really trying to reach. And so today we're going to focus on UNH's part in this exciting endeavor and look at our work bringing autonomous surface vessels and new visualization techniques into the mix. And as Tara mentioned earlier, our lab has for many years been developing new approaches, new applications, and tools for seafloor and water column mapping. And we're always looking for ways to try to do things better and more efficiently. And in the past few years, given the advances in sensors and computational ability and machine learning techniques, it's become clear that autonomous, and it's not really proper to say autonomous right now, at least for what we do. Our systems are really uncrewed. They're not fully autonomous. We hope to get there someday, but for now we'll call them uncrewed systems. They have the potential to be a game changer in the world of offshore exploration. And to understand why, let's take a quick look at what the costs are associated with operating our large research vessels. And if we look at this distribution of costs, we see that a large portion of the operating costs is associated with the crew. And this, of course, implies that if we had uncrewed vehicles, we have the potential for large cost savings. But the use of uncrewed vessels offers a lot more. They offer the opportunity to be a force multiplier and thus truly increase the footprint for things like mapping operations. And they offer the opportunity to carry on work in perhaps dangerous areas or bad weather conditions where crews would get seasick and be uncomfortable, and operate 24/7 for many, many days at a time. In the world of robotics, they like to call it the 4Ds, dull, dirty, dangerous, and dear in the English sense, expensive. Now, I would never say that mapping is dull, but it can get monotonous sometimes. And so for these and many other reasons, as we look to the future of ocean exploration, we need to explore the potential of uncrewed systems. Our colleagues at Woods Hole and USM focusing on uncrewed underwater systems, really autonomous systems in that case. And we at UNH focusing on surface vessels, which I have to say are much more recent in their evolution and development than the underwater vehicles, actually. So we're going to highlight today 3 of the uncrewed vessels that we have been working with. The first of the larger vessels that we got access to, we call Ben. It's a 4-meter-long platform. It came from a company called ASV Global, which is now part of L3. And it was originally built as a target drone, but we worked hard to convert it into a mapping system. The second system we'll introduce is one that was specifically purchased for the OECI, and that's the DRIX. And based on lessons we learned from our work with Ben, the DRIX, which was purpose-built for mapping, allows high-speed operation so that it can easily keep up with the mother vessel without compromising data quality, and for relatively long-duration missions. So we're quite excited about that within the context of OECI. And then finally, we'll discuss our work with Sail Drone in the development of a very large, in this case 72-foot or 22 meters, sail drone Surveyor, a vessel specifically designed for very long endurance deep sea mapping missions in remote areas of the world without the need for a mother vessel. And so we'll touch on each of these as we move along. And finally, we're going to visit our visualization lab, where you'll see the work that our team is doing, blending virtual reality with augmented reality and looking at new and exciting approaches for enhanced situational awareness for the operation of uncrewed vessels and for the interpretation and analysis of the data they collect. So to introduce our uncrewed systems, let me bring in Val Schmidt. Val is the lead of our autonomous systems group, and Val is at one of our ASV lab facilities not far from campus, where they're getting the DRIX ready for a mission next week. We'll be working together with Dana and his team with the WHOI Mesabot. So let me turn it over to you, Val.
Hello, everyone. I'm Val. I lead the robotics team here at the Center for Coastal and Ocean Mapping. And in a minute, I'm going to give you a tour of the DRIX. But before I do, Let me introduce you to KG Fairbarn. He's going to talk about Ben, the ASV we've been operating for about the past 5 years, and give you a quick background on that one. KG?
Hi, thanks, Val. What you see behind me, this little yellow boat, a lot of people think it's a submarine. We're really only a submarine on a really, really bad day. We are a boat. We stay on the surface. Its name is Ben, like Larry said. That stands for the Bathymetric Explorer and Navigator, and that's exactly what we do. We explore the oceans and lakes, and we navigate around there. This is a research and development platform, a little different than the DRIX. It's 14 feet long, so we can travel all over the world. It's a lot easier to mobilize in different places. We put it into our mobile lab. It's this enclosed trailer that fits Ben on its own trailer, and we can drive it anywhere we want to. And we've done that all over the place. We can also put it into a shipping container and ship it over oceans and around the world, and we do that as well. We've traveled to California in 2017. We've been to the Arctic. We shipped it out to Kodiak Island and worked off a NOAA ship in 2018. We were back in California right after that trip to the Arctic. We shipped it from Alaska down to California, been to Lake Huron and mapped the lakes around there. What you're looking at there is Nicamroro Island, where we were looking for Amelia Earhart. You might have missed Ben in there. This is a drone shot looking at the research vessel Nautilus, and we were surveying all around that atoll looking for Amelia Earhart's plane. We didn't see it. There's Ben being deployed off of the exploration vessel Nautilus. It's a very, very dynamic operation there. But a little detail about Ben, it's a 3-cylinder diesel engine, so we have a decent range on it. We can go for about 18 hours on a full tank. We have a telemetry link of about 15 kilometers. That's about 9.5 miles. That can be further or less. If there's a big ship between us, we get a whole lot less. So there's a lot of situational awareness stuff that we're developing on the vessel. You can see Ben behind me now. We have a marine radar back there, and above that, 360 cameras, a LiDAR unit, all our telemetry antennas. We have a lot of radios on here and a lot of computers on board for our autonomous systems. And that's really what we do with this. We develop these autonomous systems. It's made for research and development of them, and it works really well for that. Yeah, I'm gonna hand it back over to Val here, and he's gonna talk a little bit about our bigger, newer boat, the DRIX.
Hello, everybody. So this is the DRIX, and it's in kind of its cradle, and there's a lot of different pieces. So the first thing I'm gonna show you is a picture where we've craned the DRIX's docking system off the top of the DRIX, and it's below it in it's what's called the interface module, which is kind of the cradle that it's in here in the lab. But that's the docking system that the DRIX drives into and docks. It allows us to quickly pick it up out of the ocean and onto a ship and then deploy it back later on. So there's the DRIX and the interface module down beneath it. Okay, so DRIX is a really unique vehicle. It's 7.7 meters long and only about 80 centimeters wide. So that makes it super efficient. It has a wave-piercing bow, and it's so efficient, like it clutches in at 4 knots, and its maximum speed is something like 13 knots. So that forced us to kind of totally rethink about how we do piloting operations to keep things safe. And in a video that you're going to see here in a second, KG is practicing that very thing from this summer. Tom Spiro, one of our interns, is looking on there, and KG is practicing emergency stops to get a feeling for what it takes to stop this high-speed vehicle and how much space we got to give ourselves so that we can be super careful when we pilot it around. Okay, so of course, most of the time we don't remotely pilot it. We program it and we send it off on its own. And all the computers to do that are in the electronics compartment here. But while it's on its own, we got to keep things safe. So there's a whole slew of sensors at the top of the mast up there to do that. There's a suite of cameras that can look in all directions all the way around. There's a marine radar on this one too. It's actually the same model that's on Ben. We really like this model because it gives you both a short range radar and a long range radar in one unit. So you can see tens of kilometers away to detect big ships when they come. There's a LiDAR up there. The LiDARs give you close in, maybe 100-meter range, but lots of resolution. This summer we were picking up lobster pot floats with it without any problem, and the DRIX would deviate from its course and go around them. Also up there are some GPS antennas for navigation, and then a whole bunch of other antennas that are telemetry systems to transmit a subset of that data that we're collecting back to the operator so they can review it. But then the bulk of that data goes down into computers inside the hull of the DRIX for analysis in real time and decision making and planning for those systems to keep things safe. Okay, so that's the top. Let's talk about the bottom part. So the gondola here on the bottom is where all the sonar transducers are. There's going to be an image in a second that's going to show you a view of the gondola from the bottom. You can see circles and squares there, and those are the individual transducers themselves. We've got sort of two different kinds of sonars here. The first one is called the EK80. It's a fishery sonar made by a company called Kongsberg, and we're really excited about this sonar because it has a really low noise floor and a really wide dynamic range. And what that means is it can listen to really faint returns from really distant objects and really loud things as well. And in addition to looking at sort of fisheries kind of stuff, we can look at things in the water column. And so this image that you're seeing is our very first trip out of the harbor this summer with this sonar operating, collecting data, and we caught the really coolest data set that is a great example of capturing oceanographic phenomena in the water column. So here's an image of the sonar data itself. So the red returns in this are loud echoes, and the big red swath you see in the middle is the seafloor. The one at the top of the display is actually the transmit pulse itself. But the really interesting ones are the faint echoes, the blue ones, kind of that ramp that's going up in the middle. What you're seeing there are acoustic returns from critters in the water column and sediment and things like that that are riding on the density gradient between the salt water from the ocean on the right and the fresh water coming in from the river on the left. So this is sometimes called a salt wedge, and it's something that's well known, but it's not something that's often imaged. And of course it happens every time the tides go in and out, but that's such a neat view of that. And one of the other things that was apparent in that image is that when you have flow of two fluids of different densities past each other, they set up waves, and you can see the waves and that density gradient. It's the kind of thing that just makes us really excited because we know we're going to be able to do that in the big ocean as well, where there's different kinds of oceanographic effects. And one of the robots from WHOI, the Mesobot, is designed to look at plankton in the water column, and we can track that plankton with this sonar system. So it'll be a nice merging of technologies. The other sonar that's in there is EM2040 multi-beam echo sounder. That's a sonar that is a swath mapping sonar. It measures the topography or bathymetry, we would say, of the seafloor. This is images of data that we've collected, not with this system, but with another one on another DRIX. It's kind of neat because in the image, the close-up image on the left, you can see lobster pots all in a line on the seafloor. Of course, in New England, those things are everywhere, but these kinds of topographic maps are used for everything from seafloor characterization to establishing geotechnical studies for wind farms and of course, nautical charting to keep ships safe. Now, the other thing that's in the gondola that I didn't talk about is an inertial measurement unit. It's a fancy system that measures the accelerations of the vehicle and the rotation rates and uses that data to filter the data from the GPS. And that gives us really accurate pitch and roll and heave of the boat and its heading and its precise positioning, which we need for those sonar systems and the navigation. Okay, so let me come get you real quick because we're going on a field trip. All right, here we go. Hope I won't make anybody seasick. We're gonna walk around to the business end of the boat here. This is Basile. Basile is from France. He's helping doing some repairs. Okay, so this is the stern of the DRIX. Sorry, fellas, we're kind of in your way. You can see the prop down there on the bottom. The rudder would normally go right here. We've taken it out so that we can transport it safely and not break anything. And then this chute is kind of interesting as well. So this is where we deploy a sensor package called a CTD, and it actually happens to be sitting right here. It's the sound velocity sensor and connectivity and temperature as well. And the reason we have to measure that is sound, as it travels down through the water column, will refract as it hits layers that have different sound speeds. Refract means it bends. And so we measure profiles down through the water column so we can correct our sonar data to make sure that we don't get funny artifacts from all that bending. And up there, you can see the winch, the big giant kind of fishing reel with a motor attached to it that winches this guy out the bottom there, down deep into the ocean. So we can do all of that from the operator station over here on shore. And I think that is about it. This summer, we did all kinds of trials with the DRIX, operating it from shore daily for about 3 weeks, did training with a bunch of folks, testing all of these systems, making sure that they work, finding things that needed to be fixed that we're working on now before we go out again in another few weeks' time. It really is a unique system that we're super excited about, and we're really happy to get to share it with you. All right, I think that's it. I think we're back to you, Larry.
Well, thank you, Val. That was a wonderful presentation of the DRIX, and we're very excited about our use of it. And as Val described, there's a shallow water sonar in it now, and we're hoping that by the end of next year, we'll actually be able to upgrade that so it can work into much deeper depths, down at 2,000–3,000 meters even. And that'll be a great challenge, but it's one we're looking forward to. Before I go to the Viz Lab and turn you over to them, I want to introduce one more autonomous vessel that we've been working with, and that will become part of the OECI arsenal, and that's the sail drone Surveyor. And this is the big brother of the sail drones that you might have heard a lot about over the last few weeks, the ones that have sat, or the one that sat in the midst of the hurricane, and really remarkable in terms of how robust it was, collecting data all that time. Well, those ones are about 21 feet or 7 meters or so. This is now a 22 meter, 72 foot version of it. And if we think about the logic that I presented for using uncrewed systems, and we look back at the relative costs, we see that the other major expense of a research vessel is for its fuel costs. And that's a very variable one, depending on where we are in terms of the cost of fuel in a given year. And here, having a vessel that's powered by wind for the most part offers the opportunity to greatly reduce or even remove the fuel costs. That this one does have a small little auxiliary diesel engine to make sure we can always charge the battery or maneuver if we have to. But for the most part, it operates under wind power and with a large set of solar panels. And so this allows it to operate for really extended lengths of time, actually many, many months. And it also has a greatly reduced carbon footprint, which is certainly very nice. But now we can basically get rid of a large portion of the costs of a standard research vessel. The sail drone Surveyor is equipped with a range of environmental sensors measuring all kinds of water and atmospheric properties. And most importantly to us, both with a deep water EM304 and shallow water EM2040, the same sonar that Val showed you on the DRIX. But this also it's large enough to easily carry a deep water EM304 capable of mapping easily to 5–6,000 meters. It also has a full suite of the EK80 fishery sonars. Val described that on the DRIX. The sail drone has a full suite of many frequencies of echo sounders. And working in collaboration with Mabari, it has an eDNA sampling system. It can take up to 60 samples during a single mission. Well, earlier this summer, we put it through its initial seagoing acceptance test, and we're able to produce beautiful data in both shallow water, you see here, and in deep water. And we also got to exercise its mission portal that provides all sorts of situational awareness for truly remote operations, because these operations are almost always far over the horizon. And we got to explore the capabilities, and I have to say the limitations that we currently face of collecting, processing, and visualizing mapping data far over the horizon through satellite links. But in doing that, we also started to set up procedures for processing in the cloud, and hopefully we'll soon be working with low Earth orbiting high bandwidth satellites, all which will become key components of our OECI efforts. So it's a wonderful opportunity to kind of get an early look at those capabilities and limitations. The Surveyor left San Francisco in mid-June on its first long transit across the Pacific, and you can see the beautiful copper hull there as the anti-fouling paint has this copper component to it. There it is under, I assume that's a Golden Gate Bridge, but one of those gorgeous bridges in San Francisco. And it went off across the Pacific, very successfully collecting mapping and ENA samples the entire time. And the data were really quite beautiful. And this is really in part due to the fact that as a sailing vessel, when it's under sail, it's very, very quiet. And it gives us a quite extended swath width when it's under sail compared to when we turn the motors on. The vessel then arrived in Honolulu about the 8th of July. And you can see now that the hull is all blue because that copper anti-fouling coating has turned blue. But it was really a wonderful arrival and a very, very successful adventure. The OECI will really be putting the remote mapping capabilities of the Sail Drone Surveyor to the test next year, as we hope to spend many months mapping critical gaps in the area of the Aleutians. And as we think about these remote missions and all of our uncrewed missions, we need to think about the best and really most effective ways to provide situational awareness for the operators who may be thousands of miles away from the vehicles. And so to hear about what we're doing along these lines, let me turn it over to Tom Butkowitz, who's the director of our Viz Lab. Take it away, Tom.
Welcome to the CCOM Data Visualization Lab. Here we study how we can apply interactive data visualization to support ocean mapping and ocean technologies in general. We do everything from interactive touchscreens to 3D stereoscopic monitors, weather visualization, ocean mammal tracking. We do a lot of virtual reality and augmented reality. We have a ship simulator that we built. And then we also have this large format tile display that we use for collaborative visualization and outreach events and presentations. For example, here we're using the screen to display coverage for the Seabed 2030 project. As you can see around Hawaii, we have really good multi-beam coverage, but just a little ways away, we have massive gaps in between transit lines that are big enough to put entire US states in.
The BaffyGlobe software has been expanded with a gap filler application that assists in planning transit routes that will help fill in these unmapped areas of the seafloor. Swath widths are estimated based on pre-existing or predicted bathymetry, and lines can be automatically optimized to either abut existing lines or to increase on regions.
One researcher is how we can use augmented reality technology to increase safety of navigation. Augmented reality is a technology that superimposes a digital content on top of your real-world view. So this would have a great implication for mariners because they don't have to take their eyes off of the water to get navigational information, and keeping one's eyes on the water is the #1 factor in avoiding ship collisions. So this is a Microsoft HoloLens. It's a first-generation AR device. We got one of these and we wrote our own augmented reality navigation software for it, which is what you're seeing in the background here. But one of the big problems we ran into is it's just not bright enough to use outside during the day. Another shortcoming we found with these first-generation units is they have extremely narrow fields of view, so you're only getting digital content in the very center of your vision. And you can imagine that that cuts down on the situational awareness of the user. And we wanted to do an experiment to kind of figure out what is the strength of that effect, how much of a limitation is it, and what kind of field of view do we need out of future AR devices for them to be useful for ship navigation. To do that, we created a ship simulator using virtual reality, and in there we're able to play around with all kinds of AR overlays at the full 120 field of view of the virtual reality.
Our ship simulator allows us to conduct studies in any environment or weather condition without the expense of ship time or the danger of giving undergrads control of a real boat. Here, we are able to simulate a wide range of potential AR devices and try out different AR overlay designs without wasting time dealing with hardware hassles such as registration or brightness issues. We found that some navigational data, such as track lines, feature locations, and compass bearings, work great in heads-up displays, while other data types, such as surface currents and bathymetry, are just not very useful when displayed in a first-person perspective. We conducted a human factors study to determine the effects of restricted field of view on the usefulness of augmented reality for ship navigation. Study participants were tasked with piloting the virtual boat from buoy to buoy using both AR overlays and a traditional electronic chart display to find the target buoys and navigate between them. By using an eye tracker inside of the VR headset, we were able to measure how quickly participants located targets, how many times they took their eyes off of the water to check the electronic chart, and how much attention they paid to surrounding ship traffic and kayakers.
When no augmented reality was provided, which is the red line here, it took participants much longer to get their eyes on the target. We also saw that for wider fields of view, targets were generally acquired faster. Augmented reality overlays were very effective at presenting navigational waypoints while keeping mariners' eyes on the water. When there was no augmented reality overlays, participants looked at the ECDIS map over twice as often and took their eyes off the water for over twice as long. Interestingly, we found that field of view didn't really have an effect on this, so that tells us that even restricted field of view augmented reality devices can greatly increase marine navigation safety.
So now we're moving beyond simulating augmented reality and virtual reality, and we're trying to create a true augmented reality prototype that we can use both here in the lab and out on our boat. And we're doing that using these Nreal AR glasses. They're much less obtrusive than a HoloLens or any big headset that we have to strap on. They're very lightweight, and they accomplish that by being run off of a cell phone. So this is where the battery and the computation are offloaded to, and then I can just stick that in my pocket. And then what we do is we have the visuals from our simulation up here on our tile display, and then I can get actual AR overlay imagery within my headset. And then we should be able to also take this out on the boat, and we can use it there and just hook into the boat's navigational and positioning system.
And here's just a quick shot of some bathymetry that we're visualizing in 3D using the Nreal glasses.
Another project we're working on here in the visualization lab is how we can better support telepresence in remotely operated vehicles. What you can see here is 360 video that's streaming back from the RV Gulf Surveyor. So this allows an operator to see in every direction, and then we can view this also inside of a virtual reality headset, and we can send back high-resolution video from just the places that people are looking at. We can also send back high-resolution imagery and video for places where AI algorithm running on the boat has detected objects that may potentially be a danger. We can also overlay ship tracks and other navigational information on top of this, much the same way we do in our augmented reality platform.
Hi, I'm Drew Stevens, a recent PhD graduate and now research scientist with the Data Visualization Lab. Some of my main research interests are flow visualization and how we can use virtual reality to improve interaction and analysis of oceanographic data. Behind me is a clip from my dissertation research showing flow visualizations in virtual reality. We think that VR could be an ideal platform for ocean exploration tasks such as immersive telepresence and the control of remotely operated underwater vehicles where spatial understanding is important. With the addition of a 6° of freedom controller, you can get much more precise and intuitive control of things like underwater sampling arms from a robot.
We hope to extend our virtual reality research to provide immersive 3D telepresence for remotely operated vehicles. Whereas ROV telepresence currently consists of viewing 2D camera feeds, we envision reconstructing 3D scenes using multiple cameras and technologies such as 3D imaging sonars and flash LiDAR depth cameras. Remote operators could then view the scene around the ROV in stereoscopic 3D from any arbitrary angle. This would allow multiple live remote viewers to freely explore the underway dive mission scene, tagging points of interest for the operator to then examine in detail. Decoupling the operator's perspective from fixed cameras could also make it easier to manipulate objects and collect samples in challenging environments. We developed a virtual reality tool for exploring and measuring coral reefs that were captured using underwater video and then reconstructed in 3D using structure from motion software. This software is now being extended to include an interactive annotation feature intended to produce training input for artificial intelligence recognition algorithms. It can greatly increase the speed at which annotations can be made over traditional methods, and more importantly, it has the potential to provide more robust and useful annotations for the AI to learn from. Annotations of different species or objects are traditionally drawn manually on top of individual 2D images. This is a time-consuming process that significantly limits the number of images in a dataset that can be manually annotated. Our new VR tool allows users to annotate all of the frames of an underwater video by virtually spray painting annotations onto a 3D model of the scene captured in the video. The spray-painted annotations are then unwrapped and stored in copies of the original model textures. The model can then be re-rendered from any viewpoint showing the annotations. Since we already calculated the camera locations for each video frame, we can then re-render every frame using the annotated model. This propagates the annotations back onto all of the thousands of video frames in the dataset used to generate the model. By annotating with unique per-patch IDs, the AI will be able to get examples of how each particular instance of an object or species appears from different angles and under different lighting conditions. This improved richness of training data should promote more robust AI identification algorithms.
Thanks for joining us here in the Data Visualization Lab. Now we're going to turn it back over to Tara.
Thanks, Tom and Drew. And so now we're going to open up the question and answer period. So if you have questions, make sure to drop them in the YouTube comments. The first one I'm going to give to Val. So Val, Brian Midson, hi Brian, says, can either DRIX or Ben support a very deep water sonar like EM304, like the Surveyor sail drone?
So Ben really doesn't have the real estate, but actually a custom gondola is being built for DRIX to support an EM712. So that'll go down to about 1,000 meters roughly. So not quite as deep as the 304 at 4,000 or 5,000 meters, but significantly deeper than the shallow water multi-beam that's on there now.
Excellent. And then I had another question for you. With all of these various systems out there, how do you determine which sonar system or which system is the best one to use in each scenario?
That's a great question. I mean, to be honest, the DRIX is so new, we haven't had a choice. So this will be a question going forward. It depends a little bit on the mothership that we're going with and the mode of operation that they're thinking. So if they want to go sort of side by side with the ASV and do really long swath lines, then the DRIX is a great answer because it can keep up with a big giant ship. Ben is great for shore operations or operations where the mothership is anchored and it can go out and plot along and map the seafloor without a lot of input. So we're still sort of figuring out which system is the right one for different scenarios.
While I have you, we also have a question about are the autonomous systems using AIS, VDES? So Val, is that a good question for you to answer?
They both have AIS on them. They both have MMSIs and transmit. And if you look on marinevesseltraffic.com, you'll see Ben and you'll also see DRIX 8. Both of those will show up there.
KG, can you talk a little bit about the Ben and the sonar system that it has?
Certainly. I kind of forgot to talk about the main part of Ben because it's a seafloor mapping boat. We do a lot of navigation around the lakes and oceans, but its main feature is the sonar. And let me get away from here because right underneath it, you can't see it right now because it's on a ram. Similar to DRIX. DRIX has a gondola underneath it, kind of like a sailboat keel that goes down, and Ben has kind of a smaller one that doesn't go as deep, but it's on a ram, and it comes down here and drops down and has a multi-beam sonar on it, very similar to the one that's on DRIX. It's an EM2040 made by Kongsberg. Yeah, so we're well below the waves there, and we can map the sea floor.
Actually, KG, what actually is AIS and VDES for those like me who don't totally know?
So AIS is the most people say AIS, but I want to say autonomous identification I'd have to look it up myself. The A is something. Identification system. It's how boats identify themselves at sea. So a lot of boats are only receiving. So a lot of recreational boats are only receiving data from other boats, but commercial boats, especially big ships, are required to transmit and receive, and they transmit their speed, course over ground, the name of the vessel. The bigger ships have even more information on where they're coming from, so it's a really rich data set for autonomous vessels to grab and find where it is automatic ID system. Someone's telling me that's what I wanted to say. And, I didn't want to say it because I thought I was wrong, but that is the automatic ID system there. But it's a very, very nice thing to have when you're out there, because we have radar targets, we have LiDAR, we have cameras. But AIS, if you're transmitting AIS, we know exactly who you are without looking at a picture of it. And your course over ground speed, all that information is transmitted over a VHF channel that we can get for, tens of kilometers away, pretty much line of sight, depending on how high your antenna is. So it's a nice thing to have.
Excellent. Thanks, KG. And happy birthday. Another question that we had that came up, can you say something about data volumes for this really cool video rendering with overlays? Is that, I'm going to ask Tom or Drew. How about Tom? There we go.
Yeah, I assume that we're talking about the live video feeds from ROVs and also from surface vessels. So what we're doing with that is we're trying to outfit Ben and other ASVs with 360 cameras. So we're pulling in imagery from all directions in very high resolution. The camera we're using right now is an 8K camera. So you can imagine that's a lot of data volume. And what we're doing is we're trying to come up with some kind of viewpoint dependent compression techniques. So they have limited bandwidth between the ship and shore. And so right now, they'll send the camera feed for every direction, but it'll have to be at a low frame rate or a low bandwidth rate. So you'll have less resolution. And what we want to do is, take places of interest within that 360 image and send those back at high resolution. And then we can kind of cut down on the resolution and the data rate that's being used for places that we don't really care about. So we can send the sky and we can send looking down at the boat, but we could send those at low resolution, or we could send them at 2 frames per second. Whereas stuff that's on the horizon, or if we're using a virtual reality headset to view the feed, then we can send back super high resolution data for just where the viewer is looking. And we can also look at the AI identification of objects in the water. And if the AI says, hey, there's something in the water here that you need to watch out for, it can send that bit of the 360 image back at high resolution and kind of make the viewer aware of that. So that's kind of how we take, big 360 8K video and try to cut it down so that we can send it back to shore, and then we reconstruct it at shore to give you an immersive kind of presentation there.
That's great. Thank you. I know Larry Mayer also wanted to comment a little bit on that question. Larry, are you there?
Basically, I wanted to first compliment Tom and the crew for all the effort they've put into trying to compress these tremendously high bandwidth signals to fit in the limited pipeline that we have these days, but also to say that I truly believe we're at the cusp of a real large change in our ability to transmit information from sea. And that's with the new generation of low Earth orbiting satellites that are gonna, I think, really start giving us near internet type bandwidth from remote vessels far offshore. And I think that is going to be such a game changer. And I just can't wait to get there, because we do spend so much of our time thinking about how to compress things and how to put a lot of information into a very small pipe. But hopefully that pipe is going to open up quite a bit soon.
Great. I actually want to go back to Tom to touch on what you've just mentioned, Larry. I know, Tom, you had said that you were interested in having more people contribute media materials and things like that. Can you mention, talk a little bit to that?
Yeah, so when we start thinking about how we can do immersive telepresence for ROV missions. The biggest challenge for us is, data availability. So having either, multiple cameras on a ROV that are all calibrated so we can calculate a 3D scene from that, or using some more advanced technology such as like 3D imaging sonars or flash LiDAR cameras, something like that that allows us to reconstruct a scene in 3D in real time. And then also, having data available that we don't generally have recorded, such as positioning of robotic arms. So kind of, what I would love to do is kind of recreate a scene. So instead of watching from first person perspective of one camera, that you can turn the view and look from the side. So you can see how you're manipulating this robotic arm. And I think that that'll be a much more powerful interface. But we really need people that are out there doing this work to kind of work with us to get us the data we need and maybe try out some new sensors.
While I have you here, Tom, we have another question that's come up. Do you have data or information from users that characterizes how VR operations compares to actual helm maneuvering?
We haven't actually tried it yet, so I don't know.
Okay. Well, stay tuned for that. We have another question. I'm going to ask Larry this one. How does the sail drone power the sonar, radios, etc.? Is it solar panels?
Yes, it has a very large area of solar panels, and it does, like I said, have an auxiliary diesel to charge the batteries if necessary. But I believe, and I think and you can see on this image the large area of solar panels. I believe that they can generate about 5 kilowatts of power, which is more than enough to operate the sonar and all the other sensors on it. And if there's anybody from Sail Drone out there, I'm sure they'll correct me if I'm wrong, but if I remember correctly, it's about 5 kilowatts that are generated.
I have another.
I could tell you that the EM304 it takes about 3 kilowatts, so you see there are 2 kilowatts to spare. So.
I feel like it's like a Apollo 13 where they're trying to figure out how much power they can get out of the LEM. I have another question here for the Viz Lab. So can the visualizations also be used by people who don't have the cool glasses and the cool tech? I know that my son is asking for a lot of VR stuff for Christmas, but how accessible is it to people who don't have all of the gear that you have there?
Yeah, so it's pretty accessible for the most part. Like the coral reef stuff, we've built out WebGL versions of that'll run in your web browser. You do have to have a fairly powerful computer to run it because it is very graphically intensive, but it'll run on a standard desktop. The thing that you really miss out with when you don't have a VR headset is the stereoscopic 3D. So that really lets you kind of perceive the 3D structure of the scene. And then also the 6 degree of freedom controllers. So being, whenever you have an inherently 3D task, having an actual 3D controller really makes a difference with, having accurate interaction with that scene. Just the 3D stereo has always been challenging. We used to be able to get 3D monitors fairly cheaply. Now they're very difficult to find for a reasonable price. But VR headsets have really come down in price. So for a few $100s, you can get something that will really do a very good job. And those augmented reality headsets that we were using, that Nreal one is somewhere around $600 right now, and it uses your phone for the computation and everything. So things are becoming more affordable. But again, a lot of this stuff can run on a desktop, like the ASV 360 stuff. We're planning to make a standard desktop viewer for that as well. So you don't have to use virtual reality or fancy headsets. It helps.
That's great. I wanted to ask a little bit. The ocean visualization is not something that you see in a lot of schools that's offered as a program. So like, how did you both get into this specific field? Like I know Drew especially has taken a very kind of not classical way to get here. So what made you want to follow this path?
Well, for me, I kind of discovered data visualization and really became attracted to it, a way to take things that is, essentially just data, ones and zeros on a computer hard drive and make that into some useful information. And so that really spoke to me as a, a domain I wanted to work in, and I found that CCOM studied that in the context of the ocean, and I've had a lifelong love of the ocean in addition. So being able to marry those two interests into one research discipline sounded pretty darn cool to me, and so I followed that, and it has been a very rewarding experience, and we learn a lot and get to use a lot of really cool technologies to, essentially see things that nobody's ever seen before, and that's very exciting to me.
And I'll mention that we're going to be at the Ocean Sciences meeting and demoing some of these things. So if you're planning on being at the Ocean Sciences meeting, come check out our booth there. Are there any kind of are there any barriers or challenges that you have with getting the data that you need and things, or with the technology itself?
I mean, just getting data is usually the hardest part, and then technology is fine for the most part, but none of it is usually designed to work out on the water or outside. So most of the AR headsets and things, they're just not bright enough to use outside. They're not designed to work on a moving platform. Although just recently Microsoft did add a moving platform feature to HoloLens 2, but up until then, one of the biggest problems of a lot of this technology is that they use a combination of optical sensing to figure out how they're moving and internal motion sensors. And so when you're on a moving platform like a boat, and you're inside the boat, the headset will not see any motion because that's not changing, but it will be feeling the wave motion. And when those two sensor streams conflict, it really causes some problems with the devices. So that has been a challenge.
That's great. Awesome. I think we should probably shoot our last question over to Larry. So Larry, what are kind of the plans for all of these vehicles over the next several years? Where do you see everything going?
Oh my gosh. Okay. Well, I think we're really just kind of setting the scene here for just a spectacular extension of our capabilities and abilities, and I truly envision a time when we're going to have distributed systems that are communicating easily back to shore. I think a lot of these systems will be able to start operating from shore. We saw the beginning of that with the tech demo early on, that we'll be able to go out with maybe one mothership and multiple platforms communicating with each other. Just super optimization of our overarching goal of exploration, characterization, and mapping. And I think that there's no limit. And I think if we go onto the visualization side, I think we can have both the operators, the scientists, and the general public be immersed in what we're seeing. And I think we're gonna just put the space programs to shame. We're really gonna demonstrate what can be done on our own planet.
That's awesome. Well, that is great. Thanks everybody for joining us today. Oh, yeah.
Yeah. Well, I didn't realize if you wanted to sum up, I wanted to show one more slide, because that's the slide I wanted to show. Because not only is it a beautiful picture. This is the sail drone heading off on its mission to Hawaii. But I know the tradition has always been in the oceanographic community that the last slide is usually a sunset, but this is a sunrise, and I think it really sums up what the OECI is all about. And it's just the beginning. We're just really starting on really opening up this world of exploring our planet and exploring the oceans. And so, no more ends for us. It's the beginning.
That's great. Thanks, Larry, and thanks to all of the other folks here at the University of New Hampshire. If anybody has questions that we haven't had a chance to answer today, just feel free to reach out to us, and we're happy to answer them. And I will kick it back over to Aurora now.
I'd like to thank our hosts today, Tara, Larry, Val, KG, Tom, and Drew from the Center for Coastal and Ocean Mapping at the University of New Hampshire for giving us a really wonderful glimpse into their work. On behalf of all of today's guests, I'd like to thank you very much for joining us to learn more about the Ocean Exploration Cooperative Institute. I'd also like to thank all of our OECI partners and NOAA collaborators who make this work possible, especially the University of Rhode Island's Inner Space Center, who produced this webinar. This webinar is the fourth in a 6-part series highlighting the amazing work of OECI, If you've missed any of our previous programs, they're all linked along with upcoming webinars at the address on your screen. I hope that you'll join us for the next session, which is on November 13th at 3 p.m. Eastern Time for a webinar titled AUV Orpheus, Enabling New Exploration and New Questions in the Deep Ocean and Beyond. That will be hosted by OECI partner Woods Hole Oceanographic Institution. Thanks again for joining us today, and we hope to see you next time. Have a good day.